When we build distributed systems, we often operate under a comfortable illusion. We assume that because multiple machines share a database, they all see the exact same reality at the exact same time. In reality, unsynchronized data moving across a network is chaos. Without strict architectural rules of consistency, packets arrive at different times, creating conflicting versions of truth across your network. This standard analytical framework diagnoses that chaos. It maps 4 independent processing nodes, P1 through P4, operating on their own timelines. We start at time 0. Before any operations, all 4 timelines agree on a baseline state, sharing a variable x set to 0. Here is the central paradox. Even though P1, P2, P3, and P4 are nominally sharing that identical variable x, these parallel tracks are physically isolated. When one node makes an update, the others do not instantly know about it. This physical delay requires us to establish consistency models. These are the strict contractual rulebooks that dictate exactly when and how memory updates cross the boundaries between these parallel timelines. There are 5 specific models we use to control this flow. They exist on a spectrum, ranging from strict real-time synchronization down to completely decoupled manual triggers. Understanding these 5 models gives you the exact blueprint for a critical engineering trade-off. You are deciding, at the architectural level, whether your system must prioritize absolute truth or maximum speed. We start at the strictest end of the spectrum with linearizable consistency. It forces a distributed network to behave exactly like a single, unified machine. Looking at our timeline chart, process 1 updates x to 10. Under the linearizable rulebook, this generates an instant vertical propagation. All other processes immediately read x as 10. No delay is permitted, perfectly maintaining real-time order. The cost of this perfect synchronization is a massive computational bottleneck. Enforcing global real-time order across thousands of physical servers creates severe latency delays. To regain that lost processing speed, engineers step down to the first compromise, FIFO, or first in, first out consistency. FIFO abandons global synchronization entirely. Instead, chronological order is strictly maintained only relative to the specific process that authored the data. Returning to the diagram, watch what happens when process 1 executes a rapid sequence of writes, setting x to 1, 2, and 3. Because these writes originate from P1, the FIFO rule dictates they arrive in that exact sequence. But watch what happens when a competing write occurs simultaneously. Process 2 executes its own write operation. FIFO does not enforce a global rule linking it to P1. This new write interleaves completely differently across the P3 and P4 timelines. Process 3 and Process 4 are now permitted to disagree on the chronological timeline of events. They respect the internal order of P1's writes and P2's writes, but the combination of the two is completely out of sync globally. Moving to FIFO trades singular global truth for raw network performance. Parallel systems will experience interleaved events in entirely different chronological orders. In some architectures, even the background tracking required for FIFO is too computationally expensive. The system cannot afford to constantly broadcast updates. This introduces weak consistency. In this model, updates sit in absolute isolation. No data propagates across the network automatically. On the timeline, P1 updates x to 50, but when P2, P3, and P4 attempt to read the variable, they fail to see the new data. Their read nodes flash red, returning the old value, 0. The system does not generate an error. The other processes are actively operating on obsolete data, completely unaware that a newer value exists. To shatter this isolation, the programmer must code an explicit manual synchronization command, a sync point. The millisecond that sync point is crossed, the network floods with updates, to accuracy squarely on the developer to perfectly time those manual sync triggers. When a global manual sync is too blunt, we use release consistency, a model built entirely on precise peer-to-peer operational handshakes. Looking at the new timeline, P1 executes a write. To make this data available, P1 must push it out using a specific release operation. Process 2 must execute a deliberate acquire command before it can successfully read the updated variable. Bypassing the handshake fails completely. Process 3 attempts to read the variable without an acquire step, and it is instantly fed the obsolete data. We can drill down even further. Entry consistency takes this micromanagement to the absolute lowest level possible in a distributed system. Entry consistency abandons broad synchronization entirely. Instead of locking entire processes, it pushes control down to the individual variable level. This timeline expands to show two separate variables, x and y. Process 1 updates x to 200. Process 2 specifically requests a lock exclusively for variable x. The system performs a surgical extraction. Only x flows from P1 to P2. Variable y remains untouched. By locking only what is needed, the system prevents unnecessary data transfer. Processes working on completely different tasks never interrupt each other with irrelevant updates. The trade-off here is the computational overhead required to track thousands of individual variable locks rather than executing a single system-wide sync. These models provide immense architectural control, allowing developers to expend precious network bandwidth exactly when and exactly where a specific operation demands it. To ground these abstract timelines, we can map all 5 rules onto an everyday interface, a standard group chat. Linearizable, messages appear instantly for everyone, while FIFO keeps texts strictly ordered. Weak consistency requires a manual pull to refresh. Release, messages populate upon opening chat. Entry, only the clicked thread updates. While the chat analogy is simple, it precisely mirrors the back-end logic. The architectural model you choose directly dictates your end user's perception of now. This chart synthesizes the behavior across the 5 architectural models. Linearizable enforces absolute, instantaneous real-time updates. FIFO preserves the author's exact sequence, but permits chronological chaos globally. Weak consistency demands a hard, manual system synchronization. Release relies on explicit operational handshakes before data moves. Entry micromanages data transfer, down to the individually locked variable. If you are testing this behavior or preparing for an exam, the only accurate way to prove system output is to draw out these timelines. You must map exactly when each independent process is permitted to see an update, because as we establish that time 0, shared memory in a distributed cluster is inherently unstable without these strict contracts. Despite the entire system sharing identical data, the specific rulebook you choose guarantees an entirely different view. And that is the precise reality of consistency models.